In this video we take an introduction to the titrations of polyprotic acids. Now we're not going to be doing any explicit calculation because that's the body of analytical chemistry, but it's interesting to think about what happens at the molecular level when you're titrating polyprotic acid with a strong base. Right, so as an example for a polyprotic acid, we're going to use a generic H2A acid which has two protons. Right, so if our acid is H2A, then the two equilibria that are pertinent to the acid-base properties would be the first proton dissociation equilibrium to H plus HA minus, and then you will have that the second proton may dissociate in a second step to generate H plus and then the dianion. Alright, so then the question is, well, how does a titration curve of this acid with a strong base look like? Alright, so we can think about that as follows. Here's the pH, and here we have the volume of added base, which has to be strong. Alright, so at the start of the titration, we simply have a solution of the diprotic acid, and the pH of that solution can be calculated using ice diagrams for both processes. Okay, so we have learned how to do that earlier on in prior videos, and we're not going to repeat that here. But that's something that you can calculate again from ice diagrams. Then, as you start to add base, the titrant, which is a base, then what will happen is that you're displacing the equilibrium towards the right here. Right, so the amount of original acid will diminish, and the amount of the conjugate base, HA minus, will increase. And at exactly half the first equivalent point, then you reach something that is called a buffer. There will be a point during the titration where the amount of the conjugate base of the acid will be exactly identical to the concentration of that acid. Right? So then what will happen is that the curve will rise, but eventually you will hit that buffer, and then it will level off. It will rise very, very slowly. Okay, so that's what happens here. At this particular point, you have what we call the H2A, HA minus buffer, and right at the half equivalence point, first half equivalent point, then you will have that the pH will be equal to the pKa sub 1. Okay, and those concentrations will be exactly identical. Well, if you continue to add a strong base, you're titrating with a base. If you continue to add base, what will happen is you will continue to displace this equilibrium to the right. Okay, and eventually you will come to the first equivalent point. So that is the point where you have added just exactly the amount of base that you need to fully react the first proton of this acid. Right? So at that point, there's no more H2A left, and the only thing that you actually have in solution will be your HA minus. At that equivalent point, the pH curve turns up. Right? The pH is changing very quickly. And again, that is what we call the first equivalent point. And the main species in solution should be HA minus. That will dominate all of the solution. All right, but then you can continue to add base because you still have one proton that can be stripped of that HA minus weak acid. Right, so well, you continue to add base, and then what will happen is that you will start to pull the second equilibrium towards the right. Right, so you're neutralizing that protons, which means that equilibrium gets to the right, and then you start to decrease the concentration of HA minus and start to increase the concentration of that conjugate base until you reach the second half equivalent point, and that is where you have the HA minus A2 minus buffer. Okay, so then the curve will taper off, and here you have your other buffer, where at solution you will have reasonably equal amounts of HA minus, A2 minus, and that is a buffer. And as we know, buffers resist the addition of strong base or strong acid very well, and what that means is that the pH is not changing very quickly when you're in that region. Eventually, you consume all of the HA minus as you continue to add base, and you can reach the second equivalent point. And at that point, you have added exactly the same moles of base as the moles of the two protons that you have initially in that acid. Okay, so the curve continues to go this way until you reach the second half equivalent point, second equivalent point. And at this point, what you actually have in solution is mostly A2 minus. Right, so all of the acid has been consumed. That is what happens at the first equivalent point. Then all of this acid has also been consumed. That is what happens at the second equivalent point. And from there on, you simply have that the dominant species in solution would be A2 minus. Okay, you keep adding base, and then eventually you will get to the asymptotic limit, where you will get that the pH there will be the pH of the base that you're using to titrate. Alright, so in this video we have seen a qualitative description of how the pH curve for the titration of a diprotic acid looks like. Here is not so important to recognize what equations to use to calculate the specific pHs. What is important is to recognize the shape of the curve and then the dominant species that you have in each section of the curve.